Welcome, everyone. So our first speaker of the afternoon is Lukasz Szpruch, who is a reader at the School of Mathematics at the University of Edinburgh and the program director for finance and economics at the Alan Turing Institute, the National Institute for Data Science and AI. At Turing, he is providing academic leadership for partnerships with the National Office for Statistics, Accenture, and HSBC. He is the principal investigator of the research program FAIR on responsible adoption of AI in the financial services industry, and is also a co-investigator of the UK Centre for Greening Finance and Insurance. Before joining Edinburgh, he was a Nomura Junior Research Fellow at the Institute of Mathematics, University of Oxford, and a member of the Oxford Mann Institute for Quantitative Finance. Lukasz's broad research interests span probability theory, stochastic analysis, and theoretical machine learning. He's currently researching on the mathematical foundation of deep learning, mean field models, inverse reinforcement learning, game theory, sampling and optimization algorithms, computational optimal transport, and the theory of gradient flows. And he's also interested in applications of these areas in finance and economics. And today he's going to be speaking to us about neural SDEs, deep learning, and stochastic control.
Thanks a lot, David, and thanks a lot, David and Sebastian, for inviting me to present this work. So I want to talk today about one topic, but split into two different parts. So I'll talk about an idea called neural SDEs, which is a way of combining neural networks with more classical quantitative finance models that we are familiar with. And so this is just an example of that. And then about halfway through, I'll switch gears and I will move more towards mathematics and show you how the mathematical tools that we are using in quantitative finance, such as stochastic control, can be actually used to understand or shed some light on deep learning, why it may work, and whether we are able to provide some theoretical guarantees for some of those methods. There are still widely open questions, but I'll show you one perspective and one line of work that I'm quite excited about and I think is interesting. So, like I said, three things. I'll start with this neural SDEs as an example of generative modeling, and then I'll very quickly show you the key ideas behind mean field perspective on deep learning, and then I'll move to actually a paper that I co-authored with a colleague here in Edinburgh that shows how one can combine ideas coming from reinforcement learning and classical stochastic control together. So without further ado, this is a slide that sort of organizes a little bit how deep learning techniques and machine learning are coming to the quantitative finance. We've wrote an essay/paper on that with Samuel Cohen and Derek Snow called risk of black box models. You might have a look. There's no mathematics there, but we try to organize some ideas how they work. And so here one can think about two strands, at least the way I see it, that deep neural networks are being used as a numerical tool to accelerate things that we've been doing before, doing this faster, more efficiently in bigger dimensions, but purely numerical tool. So just a couple of examples. There's a huge amount of work in literature at the moment. So one of the first papers from the times where deep learning became popular, of course, there were people experimenting with neural networks already in the 90s. Was Hernandez, and he showed that one can use neural networks to significantly improve speed of calibrating models. And following that, there was a huge number of work concentrating around approximation of high-dimensional partial differential equations. And so I think one of the first paper was Arnold Jensen, WNE, and then others extending that work to more complicated PDEs in a more complicated settings. And those PDEs do appear in finance quite often, because whenever we use stochastic differential equations to models underlying assets, then PDEs typically will give us a solution to pricing operators when we're trying to solve stochastic control problem and follow dynamic programming principle with the right Hamilton-Jacobi-Bellman equation, and that characterizes the optimal value function. That's again a PDE. And so we can write those models, but up until recently, it was challenging to approximate those solutions numerically when at least dimension of the problem was high. And now those neural networks seem to be doing a pretty good job. Again, a very interesting paper by Blanka Horvath and co-authors, again on calibration, where she showed that one can use neural networks to approximate the parametric pricing operator. So you have a pricing operator for your model that depends on the parameters of your models, like drift, volatility, and so on. And if you approximate this, then you can very quickly calibrate the models, and the calibration often is this bottleneck in finance, where it's, if you want to use standard Monte Carlo methods, for example, this can be quite slow. PD methods again work better, but in smaller dimensions, and you get only explicit or semi-explicit solutions for specific problems. So that was interesting. And then another paper that appeared that people started working on quite a bit on was deep hedging. So Hans Bühler, Josef Teichmann, and others. And again, here the idea is that neural networks is used as a numerical tool. You can approximate your hedging strategy with a neural network and efficiently solve high-dimensional optimization problem. So that's one strand, using machine learning as a numerical tool. But there is also a second strand, the one I'll talk about today, in using those more sophisticated machine learning models, deep learning based models, to actually construct new models, more data driven, and this sometimes goes under the name market generators. And the motivation is a kind of two. One is to try to build a new, better models, or try to maybe have more systematic way of building models. I'll explain a little bit later what I mean by that. And the second is that as we are building those numerical approximations for various things in finance using neural networks, these are quite data hungry. So for example, deep hedging, you can set up your hedging problem is just an optimization problem, which you need to train with some data, and you actually might not have enough data. And one way to do that, you can train your models, find your hedging strategy by on synthetically generated data, synthetically by a model or by another machine learning tool. And yeah, modifications. One related paper to what I'll be talking about today is again Josef Teichmann and Krista Kushero. They show that one can slightly modify a classical stochastic local volatility model by approximating so-called leverage function with neural network. Again, that gives slightly different model than the classical stochastic local vol, but allows you to calibrate this without the need of computing to pure volatility, which numerically can be quite unstable. And a very recent work coming from Oxford, Samko and Christoph Reisinger, show that you can use these ideas of neural SDEs that I'll talk about today to actually fit the whole market model, where you include you're not only modeling your underlying asset prices, but you're also directly modeling the prices of traded options. So this is really interesting, really high dimensional problem. And again, conceptually, theoretically, people had some ideas how to model this in the past, but now we are gaining computational tools that allow to do that. Okay. So this was just a kind of a quick split how things can be organized. So I want to talk about generative modeling and more broadly modeling in finance. So the great challenge in finance is, of course, a model selection, and unlike a physical reality where we can do experiments in a control environment and build our understanding how the physical world operates in finance. This is lots of feedback loops and lack of stationarity. It's really challenging to build good models. But what we've been doing so far is, you take a data, you collect your data, you run some statistical analysis, and you try to see some patterns, stylized facts. And once you have that, we build or handcraft using a kind of more languages in machine learning community, some features that or build a model that can actually match those feature statistical properties that you observe in the data. And once you have that, you can recalibrate and you backtest this with data. And if it doesn't work, you go back to the drawing board and maybe add some other feature to your model that can capture some of the phenomena you're interested. And this process is quite tedious and it's difficult. And using example of quantitative finance, you can think about models starting from simple Black-Scholes and then going to local volatility, stochastic volatility, and whole family of Heston's, Rav-Bergoni, many different models, and people have been changing and updating them and making them a bit more complicated, for over the last 30 years or so. But this process is a little bit ad hoc. You just pick certain statistical properties that you think are important, and then you try to build relatively simple model with a few parameters, and one-on-one statistical learning that we've learned tells us that we shouldn't be building models that are too complicated, have too many parameters, because you typically will overfit. So that's a classical paradigm. The advantages of that is that you end up with a simple model that you understand how it works, that doesn't have too many parameters, and therefore the hope is that you should be able to fit those parameters relatively easily. And there is several decades of underpinning research. These models been built by people from generation to generation. Lots of research went into that. Unlike those, the disadvantages, that I would argue that this, what I just said, that there's lack of systematic framework for model selection. You pick some features, you pick one model over the other, but this is a little bit ad hoc often. There is, of course, nighting uncertainty that you build a models that have inbuilt randomness, and therefore they model things that change randomly, but that is very hard to detect, or it may be very hard to detect the things that are not captured by your model. So there is a large body of work on that as well. And because those models, the classical models, they don't have too many parameters. If there is some change of the regime in the data, they might not be expressive enough, and you might not be able to calibrate them, and then you need to change. So on the other completely different end of spectrum is what is happening in machine learning community. However, for slightly different applications that typically in finance is this idea of generative modeling, and two prime examples of that are general adversarial networks or variational encoders that seem to work quite well in high dimensions. And convenient way of thinking about this is using sort of framework of optimal transport. You can think that you start with when you build a model, you start with some latent distribution mu. So let's say in the context of finance, this could be DRAG, the price of your underlying asset today. And you want to build a model that is calibrated to market data, so that when you start today, the model will generate some distribution, say nu, that is implied, that you can imply from liquid options traded on the market. So that's a classical approach to calibration. So you do that, and so you can think about that process, this model that you're looking for as a transport map that takes you from this initial distribution mu today to, in the context of finance, to the distribution nu induced by options traded on the market. And the way to do that, when you want to abstract things a bit, is you consider some parametrization of this transport map T. And this could be neural network and is neural network in machine learning community, or it could be, your favorite Huston model used in finance. So once you have that, the idea is that then you're trying to find a parameter, you seek the parameter theta star, so that, I'm transporting my latent distribution into distribution I want. But then you need to measure somehow how good fit you can get with the model T that you've picked. And again, you need to choose a metric, and one choice, a popular choice, is to look at the difference of expected values. So this guy here will correspond to expected value of some function f with respect to the target measure. And this expectation here is expected value produced by the model that you're working with some parameter theta. And to make things a little bit more interesting, you also want to typically, at least many metrics in machine learning do, take a supremum over all possible values of this function f. By possible, I'll give you a little bit more detail in a moment. So if this class k over the supremum of the function, the class k from which you pick the supremum is a class of one Lipschitz functions, then this d will be nothing as Wasserstein distance. If this k is a set of bounded functions, then this d will be nothing as a total variation. But you could be in finance, you might have a bit more specific application, and maybe this k will be the set of some options traded on the market, and you are interested to find a model that prices all those options simultaneously, and that will be the choice of your metric. So while I'm showing this on one slide is to emphasize that there are modeling choices that we are making in that process, and those modeling choices are the metric that we pick when we train a machine learning model. Of course, the parameterization, so the model itself, that's kind of the obvious one, but also, and that especially in the setting where we work with deep neural networks, which have huge number of parameters, highly over parameterized, the algorithm used for training. So it's that shift that in classical learning theory, we typically were working with models. We're seeking models. They don't have too many parameters, because we know that, like I said, if you have too many parameters, you overfit. If you have too little parameters, you underfit, and you were looking for the sweet spot. In machine learning applications, deep learning applications, often the models we are working with have more parameters than even the data points that we have to train them, which means that we have a whole manifold of possible solutions, possible sets of parameters that would give you good fit to the data. So again, from classical statistical learning theory, that doesn't much make sense, but we lose that uniqueness, and somehow the things still work. We're not overfitting, and the reason for that, well, no one fully yet understands. So this is a big theoretically, it's not fully. I wouldn't even say no, it's not fully. It's not understood. It's not understood at all. We pick those stochastic gradient algorithms that induce noise during the training, and somehow out of all the sets of parameters, possible parameters, select the ones that we hope work well, generalize well. And as we know, there's multiple examples showing that this can work. But you see the contrast, going from one small model and having a big model risk to starting with a big class of possible models, and then selecting one in some kind of opaque way by taking a combination of what model I choose, what neural network I choose. This is this T, what metrics I selected to measure the distance, a fit, and the training algorithm. So very quickly, this generative modeling based on neural networks can be very expressive. Of course, you have many parameters. You can fit data very well. Very data driven because the model is so rich. Even if there is shift in your data, you can very quickly retrain, recalibrate the model, and still get a good fit. You can revisit many classical financial problems from that perspective, but there are disadvantages, and you end up with a black box model, so to say, that the parameters, they lose their meaning. We may need a lot of data to calibrate them, and again, in context in finance, there are certain things that, sorry for typo, there are certain properties that we understand well, like, we want to have models that do not admit arbitrage. We want to have models that will allow us to easily change from pricing measure to risk neutral measure, to market measure, and so on. And those neural networks, purely neural networks based models are not models, and they don't have automatically those properties. So there is actually a lot of research in quantitative finance looking at this challenge of, or appreciating that working with one model can be restrictive, and there is this model risk, and so it postulates that maybe we shouldn't be working with one model, and we shouldn't be, in the context, for example, of derivative pricing, aiming at finding one price of the derivative, but we should be looking rather at interval estimators. And so the idea is that we take a whole class, and again, in the context of quantitative finance, we take a whole class of possible models that are calibrated to market data and that do not admit arbitrage, and therefore are martingales. And then we look at if we're interested in pricing, so we know pricing is equivalent of taking expectations with respect to the martingale measure, we're looking at the price intervals. So we take the highest and the lowest possible price given all possible models that are out there that could be calibrated to data. But in practice, these bounds can be quite big. You can imagine there is a huge number of models, huge number of martingales that you can calibrate to the data, and therefore this type of approach, vanilla approach, might not be very practical. So then the challenge is how to incorporate prior information to restrict the search space of possible models, to be able to select the models that make more sense, and how to make sure that we have the efficient algorithms to search through that space. So that puts at the intersection, we're looking at something that takes advantage of classical risk models that we understand. We would like to also benefit from this generative modeling combined with the neural networks, and also appreciate that there is a multiple models that might fit the data, and therefore maybe we need to be a bit more careful and seek the bounds versus the just one price. So idea is, and I actually strongly believe that after this initial excitement about the neural networks, what they can do, now the challenge is how to combine them with the models that we understand. That there is a lot of good things about the classical models that we're working with. So here there is a context of using this combining neural networks with SDEs based models. Conceptually, this doesn't make a difference if you work with a time series or whatever. The idea here is that you have a model. There are some parts of this model that maybe you're convinced that are right, correct, and you don't want to change them. But there may be some parts of that model that you're not so sure. Maybe they're a little bit ad hoc, and these are the ones that you'd like to learn from the data. So this is an example, just an example of this. Here we say that we believe or we want to work with a stochastic volatility type model, that there is sufficient evidence that we have that stochastic volatility models are better than just local volatility models. But what we don't know, or what we're not sure about, is that we're not sure about the diffusion coefficient, drift of the price process, and driven diffusion coefficient of a volatility process. Okay, now I could have a choice. Maybe I'm quite confident what this drift should be. It should be maybe mean reverting because I have enough data. So I'm not interested in modeling that much, but I don't know what the diffusion coefficients in those two SDEs are. So I could approximate them with the neural networks and learn them from data. So this is the simple idea. The benefit of that is that even though I'm using neural networks, the class of models I'm working with is something I'm familiar with. So in particular, I know that this model induces a martingale probability measure. If I impose a condition here in sigma that this SDE is well defined and so it's good prop that this is a stochastic integral, I know that this is a martingale. The discounted prices will be martingale. This is just a remark that SDE could be also thought of this, more abstract transport plan T that I presented, with the advantage here that you're ensuring that you adapt it to the filtration automatically. I already mentioned that, and the other ways of building those models that you can combine us with signatures and lots of many different ideas out there. And these models allow you to consistently change between Q and P, so the series neutral measure and real measure, which means that you can calibrate both to your historical data and to prices induced by the options traders in the future, and you can do that in one model in a consistent way. So that's nice. And to some extent, I would argue that this type ideas mitigate concerns that regulators may have around using purely black box solutions, because here we are still within a realm of classical models that we've been using. We understand them. We know how to check them, whether they produce martingale measure and so on and so forth. And all we're doing is we're learning just coefficients using neural networks. Okay, so how then the pricing would look like, or calibration with this. So like I said, we're interested in this price intervals in the robust bounds. So given that I have some prices of options traded on the market, so for my pay of phi I have a price p phi I, and then this is a price, this expected value is a price of this pay of phi produced by the model with where my parameters of my neural networks are theta, and I measure the distance, typically say using the square loss. I'm summing over all possible pairs that I'm interested, and I want to find theta such that this is 0. So that means that my model is calibrated. At the same time, depending whether I'm interested in upper lower bounds, if I'm interested in the lower price, I might be interested in some other derivatives, maybe path-dependent derivative that is not traded on the market. I'm interested in producing a model that gives me minimal price, but is calibrated to data, I'm interested in finding the model that produces the maximum price, the highest possible price from all the neural SDs calibrated to market data. Okay, so well-defined optimization problem, and you can write an algorithm. The way we do that, I'll go quite quickly over this. You discretize your neural SDE, of course, and then use some Euler scheme or some variant to simulate this, you pick option payouts that you're interested in. You pick prices, that's your market data. And then what you do, you simulate data. So this will be a corresponding stochastic volatility model with those parameters theta corresponding to neural networks in the diffusion coefficients. And then what you do, we do two things. Direct Monte Carlo, when we want to calibrate things using Monte Carlo, there could be quite a bit of variance, which we want to kill. And the way to kill the variance is to hedge. So recall that on the previous slide, I was saying that we would be interested in minimizing the distance between the price generated by my model and the market price. And here I subtract the hedging strategy. So know that expected value of this guy should be 0, because this is a martingale on the pricing measure. Think about this as a martingale representation theorem. And so we are building in variance reduction here to kill the variance, but at the same time, we are interested in actually learning that hedging strategy. So in that loop, what I'm doing, I'm looking for parameters of my neural SD that give me this price with some hedging strategy fixed. And in the second loop, what I do, I fix my model. And here, optimizing of a parameterization, also given by some neural network, of my hedging strategy. And I do this, and at the end of this process, hopefully, I'll end up with a calibrated model and also the hedging strategy for that model. That will allow me to hedge my exposure. Okay, some simulations. We show that this approach in principle works. So here the orange and blue lines fit to the prices, market prices. That's perfect fit. And these guys here are show you the fit to implied vols. So there should be 10. We have 10 calibrated neural SDs in yellow. So most of them give you a very good fit to the smile. There is occasional a neural SD that's a little bit off. But overall, this is a pretty good result. And here, what I'm showing you is this idea of robust prices. Again, the different maturities. So let's just concentrate on this far left top corner. So here we have this blue box plots. These are the prices of lookback option calibrated to prices for the lookback option produced by the neural SD calibrated to data. So the middle guy is just ad hoc and calibrated model, and this left and right are the ones that we are during the training we are seeking the lowest price and the maximal price, or model calibrated that gives us this maximal price, and so you see that that they're not too crazy. And this, I'm going back to my comment that for standard robust pricing, when you allow for arbitrary model calibrated to data, those bounds can be quite big. And here we're saying we are only looking for bounds within the models that are solutions to the stochastic volatility model with some coefficients. And the fit here, you see is that we're getting on prices 10 to minus 7, 10 to minus 8. So the accuracy is really pretty good. Okay. There are various extensions. You can, this was how those models can be calibrated to option prices. Once you've calibrated your model to option prices, you can find a market price of risk. That is the change of measure. Or rather Nikodym derivative, which you can approximate by the neural network. We haven't done that in the paper. My PhD student ran some simulations and he claimed it worked. And having that model, you can now learn change of measure, and that gives you this consistent way changing between Q and P. And of course, you can induce additional constraints on your parameters. You can clip the weights in the neural networks. You can, if you have some conviction what those functions should be, you can add that. So some possible extensions that we haven't done, but thought about, and I think it would be interesting to look at this. We can incorporate additional market information into those models. So, for example, if I wanted to find a neural SDE calibrated to market data such that the realized variance would be within certain bound, I could add this as a constraint to my training, and then I'm looking for a model that is calibrated to data and has these properties. And so that way you're gaining to some extent explainability of what you're doing, and also I would argue that gives you, to some extent, a systematic way of building a model. I'm looking for a model that looks like a stochastic volatility model, stochastic volatility SDE. It has realized variance within certain bounds, is calibrated to that, and is maximizing or minimizing the price of some portfolio of risk that I have. This is through that description you're gaining explanation what your model should is, and you have the systematic way of thinking about this. You could also think about some sort of adversarial training in the spirit of distributionally robust optimization, where I have my deep hedging, and now I would be generating SDEs that are maybe calibrated to market or maybe slightly miscalibrated, that are maximizing my hedging errors. And then, that way you can check how robust your deep hedging strategy could be to various market scenarios. I think it'll be quite interesting project. And another thing we actually looked in some contexts is that once you've learned those SDEs using neural networks, quite complicated, functions, neural networks that have many parameters, because here in essence you're looking for fairly low dimensional functions. You have only two-dimensional process, price, process, and volatility. You could then plot this and try to actually figure out what elementary function, if your neural network learn, maybe some polynomial or something like that, and you can hugely simplify. So you use neural network for searching a model, but then you actually can extract from it a simpler model. Okay, so this was the neural SDE finance applications, and now I want to change gears and move to more mathematical side of this talk. One thing is that I will try to show you is that these neural SDEs, we train them with the stochastic gradient descent, and I show you this works. But then there is a question: can we prove something? Provide some theoretical guarantees that what we're doing there actually will always work, or maybe we just got lucky. Maybe the data set that we picked was really nice, and then if I deploy this on some different data sets, it wouldn't work. So it is important to study those questions on a kind of theory side to make sure that we understand it well. And one approach to understand deep learning, or try to understand or shed some light on this, is through this mean field theory, mean field perspective. So 2 slides on that before I go back to the neural SDEs. So this idea of a mean field perspective on neural networks goes as follows. So we consider first relatively simple one hidden layer neural network of this form here that is written here on the left-hand side. So I have some activation function, and I have then linear product alpha times z. So z is my input to my neural network that I multiplied by some weight. I apply nonlinear activation function multiplied by some weight, and then I apply this mean field scaling. So you take a sum of all those inputs from those neurons, and you multiply it by 1 over n. So this is called mean field scaling. There are different scalings. You can multiply it by 1 over square root of n, and you get and things simplify significantly. but let's stay here. So when I do this, for this one hidden layer, you can observe that you can write it down as just expected value with respect to the empirical distribution. So this new n is an empirical distribution over weights of your neural network, okay? And once you make that observation, then you see that your neural network as a function of the measure of a parameters becomes linear, i.e. convex, not strictly convex, but convex. So what does this tell you? That here on the left-hand side, I have a finite dimensional object. The dimension is here the number of parameters that I have in my neural network. And this typically is non-convex optimized, non-convex function in parameters. And non-convexity is, of course, coming from the fact that this activation function typically is non-convex, so I will lose the convexity in alpha. But if I view this, lift this to the infinite dimensional space, and I will start viewing this as a function of a measure of a parameters, then this convexifies. And so now the idea is, can I use some mathematics to actually make sense out of this and prove some theorems about the convergence of gradient descents? And this has been done in various settings. I don't know, I'll talk about extension in a minute, but it turns out that you can actually build a classical gradient descent algorithms, minimizing this function as a function of measure, and you can prove convergence of that. And there's quite a few papers out there doing this in different settings with a little bit of regularization, without regularization, on the different structural assumptions. But this is that trick that it is possible to regain some convexity in your optimization problem. The other idea, again, I'll talk about extension of this. A step from there is then you can say, okay, this is just one hidden layer. This is not so interesting. We are interested in deep neural networks. So the model that allows us to understand a little bit what's going on in some setting is this idea called sometimes neural ODEs. That was a word that actually the name that coined by computer scientists. So you can think that I'll take my one hidden layer, and here this is ODE. At each time slice of my ODT, I will have one hidden layer. I put one hidden layer. So, if you discretize this as an Euler scheme with some, k steps, I have k one hidden neural networks put together. So this will be then the neural network, the Euler discretization with k steps will give you a model for a neural network with k layers. And here, this is a toy example that you can have an interpretation of this as the neural network with the infinite width, depth width as well, if you use a measure. So this is a toy example, mathematical abstraction that you can then use to try to understand what is going on. And advantage of that is that once you understand something about this object, you can then use the tools of numerical analysis to discretize this, approximate this measure in infinite dimension with empirical measure. You can study those errors individually, and there is a hope that you might have gained some understanding and quantify the errors that you make when you train those things with stochastic gradient descent. So maybe I can prove something that works in some abstraction that, of course, is not implementable, but then I can discretize this and understand that my approximation, something that people actually are using or not far from what people are using in practice, actually is very close to that my abstraction, and that provides the link. Okay, so that's conceptually the idea. However, here the challenge is that as we move to those deep neural networks, even though we are in this mean field setting, we are in general losing convexity. So the solution to this ODE as a function of the now measure on the essentially path space, because I'm putting a distribution of a parameters at every slice t, in general is non-convex. But the hope here is that this is the object that mathematicians working on control theory, such as Sebastian, are familiar with. And they say, hey, we know quite a lot about control theory. Maybe we can actually use some of those sophisticated tools to understand what's going on. So this is, like I said, lots of works and in literature trying to build and understand how at least some architecture of these neural networks work through the lens of this controlled differential equations. This doesn't cover everything, but at least it provides one setting when we can say something. Okay, so I want to study something even slightly more general. So you can, this was just the perspective on the neural networks. Here I am actually interested in solving a stochastic control problem. Of course, if my diffusion coefficient here is 0, then I'm back to this ODE type perspective. But as you can see, you could see from the neural SDE that I've been working with, I'm actually interested in training those. So this is the problem I'm studying. So we consider this control stochastic differential equations, but my control here is this measure mu r. So there is interpretation that this has some link with neural networks, or you can just think about this as a measure value control. If you like reinforcement learning, you know that you need to, the algorithms that work well, you need to explore. That is, you're not typically working with a deterministic controls that tell you, do this or that in given states. You have some distribution of the possible actions in your control problem, and you want to learn what's that optimal distribution, what that optimal distribution is. Okay, so this is my control, and this is my just the notation for a space of admissible controls. And a classical example of this is that if I have the special structure that my coefficients are linear in control and my diffusion squared in dimension 1 is also linear, so diffusion generator of this control problem is linear in control, then this is what people call relaxed control. Okay, so gradient flows. I think I have about, is it correct to say that I have about 20 minutes? 15 minutes?
Yeah, so, well, 15 minutes.
All right, okay, thanks. So once we have this stochastic control problem with the control being distribution nu, we can define a classical a cost function. So this is my some running cost f. This is my terminal cost g. But here in this setting, I'm also adding a little bit of entropy. I told you that from the perspective of the neural networks, as I moved from one hidden layer to this ODE, I lost convexity. And to regain some convexity, I'm adding here, potentially I'm adding entropy. If my problem that I started with was convex, I don't need this entropy. But if I didn't have it, I want to convexify it. So entropy is defined here, a strictly convex function. And here we take entropy that is with respect to some Gibbs measure with a potential ux. Think about this normally distributed. I'm interested in entropy with respect to the, say, normally distributed random variable, okay? So this is a setting. And why adding this entropy is interesting. Well, the most successful algorithms on the reinforcement learning from the family called Max and RL, maximum entropy RL, actually using this entropy regularization, or if you work with Boltzmann exploration, that's essentially very strongly related to adding entropy to your cost function. And also there's a nice result, recent result by Christoph Reisinger and Yufei Zhang that show that if you consider your control problem and you add entropy to your cost function, the control, the optimal control, becomes more regular. So we know in theory of stochastic control is that often control functions are very irregular. And so if you think now about the problem of learning, I'm trying to learn my control for the model maybe that I don't know. It's easier to learn the functions that are smooth than the functions that are not smooth. So entropy is a friend here in this setting. And just an example, so one example to keep in mind why we're studying this is this: we want to train these neural SDEs. Another example is build the links between control problem and reinforcement learning, and in particular, one application here is to understand the policy gradient algorithm. So this is an example where I start with a standard control problem with some controlled alpha and standard cost function. And the way policy gradient works, I'm trying to solve this control problem over all possible Markov controls. So there's functions that depend on time and the state. And so one strategy is, let me approximate my function with this one hidden layer neural network, for example, with some activation function. And what I'm aiming now, I will want to find the parameters, that is measure over my parameters of one hidden neural network that give me the solution to this control problem. So of course, I need to understand how well this one hidden layer neural network approximates my optimal control, and this would need to be studied. And just an example, but at least if I do it this way, then my policy gradient will become a stochastic control problem with measured value controls, and I'm trying to optimize over the measure. So this is just one example. Okay, so going back to my stochastic control problem, this is my control dynamics. This is my cost function. I then introduced Hamiltonian. So I believe there was a lecture today in the morning talking about stochastic control. So I'm sure the Hamiltonian appeared there. Which is, think about this as a diffusion generator plus your running cost. And here we are not working with, we are working with stochastic maximum principle rather than dynamic programming. And so trust me on this, if you know this, then you know this. If you don't, I'm not able to cover this. But it turns out that if we want to apply maximum principle or Pontryagin maximum principle to solve the control problem, one derives the associated adjoint equation, backward stochastic differential equation that is given here. Okay, I'll tell you what it is and when this is important. So once you have it, and that's the important part, is that we can show that if you have this cost function and you have optimally controlled forward dynamics and this adjoint equation that has solution y and z optimally controlled or locally controlled with some measure nu, then you can characterize your optimal solution to the control problem as a pointwise minimization of this Hamiltonian with those x, y, and z being fixed. Okay, so the same way as dynamic programming gives you a characterization, leads to characterization of the value function for AJB equation, here when you use maximum principle, you can characterize your optimal solution as a minimizer of the Hamiltonian with together with associated forward-backward dynamics. Okay, so once we have this, we want to minimize this Hamiltonian, and you can think about it as now we want to minimize this Hamiltonian using stochastic gradient descent. Okay, that's what people do in machine learning. They apply stochastic gradient descent, and this seems to work. So that's what we're trying to do here. So we first need to derive set of local minimizers. So I want to take derivative of my Hamiltonian with respect to control. So this is a measure, but let's not worry. It's just the derivative. And I want this derivative to be constant. Typically, first order condition tells you I want my derivative to be 0. Here, using this notion of derivative, it is a constant, but it plays it plays no role. This is how this derivative works. But the point here is that once you give me, we have a corollary that if you give me a locally optimal control for my cost function, then my control belongs to the set of first order that satisfies the first order condition. Okay. And from here, from this first order condition, you can derive that all optimal controls for my stochastic control problem have this, can be characterized, can be solved, or can or lead to a Gibbs measure of this form. So note that in principle, this is an equation because I have mu star here and mu star here. But this is sort of thing about Gibbs distribution or Boltzmann exploration in machine learning. So, I had a cost function, I've added a little bit of entropy and I'm minimizing, and that's what I'm getting. So again, for those familiar with stochastic control, in the setting of relaxed control, so relaxed control is the situation where my Hamiltonian is actually linear in control. Then this derivative becomes just a classical Hamiltonian. So that means that this optimal distribution is the exponential to 2 minus sigma square of the classical Hamiltonian. But again, if you ever work with reinforcement learning and you saw the Boltzmann exploration or entropy regularized RL, you know that your optimal control, your optimal policy is given by, again, a Gibbs measure with the exponential something, 1 over regularizer of the Q function. So you see that this Hamiltonian here plays a very similar role to the Q function in reinforcement learning. And here we have slight generalization because we have added a little bit more nonlinearity. So we have some derivative of this Hamiltonian. But, those objects are connected, and therefore you can use those tools of stochastic control to understand what's going on with reinforcement learning. Okay. So we have a Hamiltonian. We found a characterization of my optimal control. So here, like I said, this is an equation. Now I would like to be able to solve my control problem, and I would like to sample somehow from this optimal control. So this gives me prescription, but if I want to make an action, so to make an action, I need to be able to sample from this distribution. So way to do that is you can construct a gradient flow. So this corresponds to the classical gradient descent, but here we are minimizing over, I think about its densities over those distributed policies. And so we consider this equation. And in particular, we know that the aim of the game is to find a drift B such that this become a stationary solution to this equation. So the same as in a gradient flow, you construct your gradient descent, and you know that you should take minus the derivative of your function that you're trying to minimize. Here it's a little bit more complicated, so it's not maybe entirely obvious immediately how to design this gradient flow that does the job. If you don't like PDEs, you can note that this is just a forward Kolmogorov equation, and I can have associated probabilistic representation of this in a sense that I can find a stochastic process such that the law of this process is precisely this guy, and this process is given by this SDE. One thing I need to mention here, this is equation in time s, and time t is the control at time t of your control system. So this is a system of equations for each t. And so you see here that if this b will play a role of some gradient, then what you have here, this dxt, you can think about this as a noisy gradient descent, noisy in a sense that, you know, I'm telling you now, this will become some gradient, and you're adding a little bit of noise, and that little bit of noise is precisely that effect of entropy that we've added to the cost function. And now you're trying to find b, you try to find this gradient, what it is, such that when I give you a cost function, j, that cost function is decreasing along that gradient descent. The same way as in Rn, if you take a function, you're trying to minimize your gradient minus, you know, derivative of the function minimizes your cost function. So the same principle holds here. So like I said, you know, we study this because we're interested in these links between reinforcement learning, and also, you know, want to understand and provide some theoretical guarantees for training neural SDs. So what we do here is we derive, we want to compute derivative of time derivative in S of our cost function along this gradient flow. So we do that, horrible expression, don't worry about this, but we have this guy B here. And what I want to do, I want to find B such that my cost function will be decreasing along the gradient flow. And so from here, I can guess what that is. So if I choose and this B to be of this form, so that I have essentially this term, first term, and the integrand squared with a minus in the front, then I'll guarantee that my cost function indeed is decreasing. Okay, so I have a candidate. We found that my gradient in my gradient flow needs to be of this form. I will skip that. That's a kind of sketch of the proof, but I'll share the slides with those that are interested. I think the proof is the sketch is quite insightful. But I'll jump to the result. So like I said, you know, we have the using this maximum principle, we've derived the gradient flow. We identified what's the right gradient. So let me go back to the stochastic representation. So you can think about this, that for every time t, that tells me how I should control my dynamics at time t, I have now noisy gradient descent with this drift. So here, this is just the gradient of the Hamiltonian. This u was this extra regularizer in my entropy. I wanted my entropy to be absolutely continuous with respect to something with a distribution with the potential u. Think about this u as x squared, so this would be just x if this was Gaussian, or the Uhlenbeck process. And here you have some noise coming from the entropy. And this is coupled now with this forward-backward dynamics, in a way that my control is given by the conditional law of my gradient. And then I plug in this into my X, the forward dynamics, and my backward dynamics. So, okay, if you never, you know, work with BSDs, that looks like, you know, a lot of complicated objects on one slide, but let me just walk you through to show you some analogies to what actually people are familiar with using machine learning. So imagine you discretize your gradient flow in S. We have a dynamics in S. So I introduce some n particles, if you like, of my process theta at time sk. Then I compute empirical distribution of this. And once I have that guy, I can plug in this empirical distribution to solve my equation forward, because that equation in X depends on my control. So now I have an approximation of my control. I solve this forward. And then I can what you do when you do supervised learning, right? You put your thing into your neural network. You have some initial condition. You put a parameter. You solve. You see that what's the output of your neural network, and you compare it with some data point, and then you back propagate your derivatives. This Max Pontryagin principle, and the reason the neural ODE paper became famous in computer science community was that they use a classical trick of control theory, Pontryagin principle to efficiently compute the gradient. So this process Y goes now backward. Again, we solve it with this distribution of parameters, approximation of your control nu n, and then with that I can update my x, y, and z process in my gradient and move to the next step in the dynamics. And that's how the training works. So it's really mathematical way of describing what is happening in machine learning. And here we just using.
Sorry to interrupt. We should look at wrapping up within the next couple of minutes.
Yeah. Okay. I'm pretty much done. And then once we understand how this works in the this continuous time setting, it's relatively classical, at least under some mild assumptions, to be able to precisely understand all the errors in terms of number of these parameters, how many particles I use, and what's the learning rate I will use to discretize my gradient descent. If I introduce discretizations here, I can all quantify this quite precisely. This is just theorem that tells you that when I run this gradient descent, I converge to the optimizer. So that is, I'm showing that my set of first order conditions, the measures that satisfy and give me first order condition, there could be only one element, and it's a global minimizer. And if I regularize sufficiently, we can prove that actually I converge exponentially fast. And that's it. That was my last slide. So I accelerated at the end, but this is just saying, this frameworks allows you to provide some theoretical guarantees. Unfortunately, those theoretical guarantees require a lot of regularization. So this doesn't answer, all the questions we wanted to answer, but it's a step in the I believe, right direction. Okay, so I stop sharing.
Thank you, Lukasz, and sort of virtual applause. I think in the interest of the schedule, I am going to ask us to take questions offline for this, and we'll have maybe a 10-minute break and